You know, for decades, physics has been staring at a few deep, really stubborn mysteries. But what if they aren't separate cold cases at all? What if they're all connected by a single, overlooked clue, one that points to a completely new picture of reality? Let's dive in.
So, this is the big question we're exploring today. There's a new framework out there that suggests some of the deepest riddles in the cosmos might share a single, beautiful solution. Now that is a massive claim, so let's unpack it, starting with the problems themselves.
Okay, so to even begin to get our heads around the solution, we first have to really appreciate the scale of the mystery here. These are not minor puzzles, folks. These are three foundational cracks in our understanding of the universe that have stumped the greatest minds for generations.
All right, first up, the heavyweight champion of physics problems, quantum gravity. We have these two incredibly successful theories of the universe. Quantum mechanics, which is just flawless at describing the bizarre world of tiny particles, and general relativity, which perfectly describes the grand cosmic dance of planets and galaxies. The problem? They fundamentally, completely disagree on what space and time even are. And right here, you can see the contradiction laid bare. On one hand, quantum mechanics absolutely needs a solid fixed stage, that's spacetime, for particles to do their thing. But on the other hand, general relativity says, nope, there is no fixed stage. It insists that spacetime itself is a dynamic player in the game, constantly being bent and shaped by everything on it. Each theory is built on a premise the other says is flat out impossible.
So our second riddle pops up when physicists try to force these two theories together. They came up with this monster equation, the Wheeler-DeWitt equation, to try and describe the entire universe using quantum rules. But when they solved it, something crucial was just gone. The variable for time. It just wasn't there. According to the math, the universe is a static, frozen block. So, where does our everyday experience of the flow of time come from?
And finally, we have the one that feels like straight-up magic, the measurement problem. See, at the quantum level, a particle exists in this fuzzy cloud of possibilities. It can be here, there, everywhere, all at once. But the instant we look at it or measure it, that whole cloud of possibility just collapses into one single definite reality. So what's so special about looking? How does the universe decide which reality to pick? It's the central magic trick of quantum mechanics. And honestly, nobody has a clue how it's done. So we've got these three massive, seemingly separate problems, but this new framework argues they all share one root cause, an assumption so deep, so fundamental, we never even thought to question it, the role of the observer. This quote, this is the whole game right here. To say observers are constitutive means they are a fundamental part of what makes reality reality. For centuries, physics has treated the observer like an afterthought, someone looking at the universe from the outside in. This new idea says that is completely backward. We aren't just seeing reality, we're part of the very process that builds it.
And look, this isn't just some hand-wavy philosophical idea. There's actual math to back it up. A recent mathematical proof, the HUZ theorem, basically shows that a universe without any capacity for observation would be, well, boring, mathematically trivial. It would have almost no structure, nothing interesting to even describe. It seems that observers are the engines that generate the complexity of the cosmos.
Okay, so what if we just run with that? What if we accept that observers are a necessary ingredient for reality itself? How does that change the picture? Well, it turns out it changes everything. Suddenly, all the pieces of the puzzle just start to snap into place. This is the core relationship in this new framework. It suggests that our reality, the space-time we see and experience, what it calls M4, is just the surface of a much bigger, deeper structure. And beneath it lies this purely informational dimension, M theta. The best analogy? It's like a hologram. Our 3D universe is just an emergent projection from a deeper, more fundamental layer of pure information.
And with this one shift in perspective, the solutions to our three huge problems just start to fall into place. First, the quantum gravity problem, solved. The two theories aren't in conflict, they're just describing different parts of the same thing. Quantum mechanics describes the surface, general relativity describes the deep informational bulk. Second, the problem of time, gone. That deep bulk is timeless, just like the math said. Time is simply what we, as observers on the surface, experience as we move through that timeless structure. And third, the measurement problem, solved. The collapse isn't a magic trick, it's the physical process of information becoming correlated, of reality literally crystallizing through interaction.
So this gives us a totally new and kind of mind-bending dictionary for physics.
Gravity isn't a fundamental force, it's more like a shadow cast by dense information in that deeper bulk. Time isn't fundamental, it's just a measure of our journey through this information. And measurement isn't some weird intervention, it's the very process of binding information into the concrete reality we see. The universe, in this view, really is a hologram.
Now this all sounds incredible, right? Maybe a little too incredible. But for this to be real science, and not just a cool story, it has to give us something we can actually go out and test, a unique prediction that standard physics does not make. And it does. It makes a prediction so strange, it's been nicknamed stuttering time.
The logic is really beautiful. If time emerges from the process of things changing and interacting, then what happens to an object if you could perfectly isolate it from all change? Completely stop it in its tracks. Well, according to this theory, it might just momentarily drop out of time relative to the rest of us.
So here's the experiment they've dreamed up. You take two entangled particles, let's call them ion A and ion B, and you carefully shield ion A so that absolutely nothing about it changes. Nothing. Meanwhile, ion B is just out there, interacting normally with the world. Now, standard physics is super clear on this. When you bring them back together, their special connections should be perfectly preserved. But this new framework, it predicts something wild, that ion A will have literally aged less than ion B, creating a measurable lag between them.
And this is the clincher. The theory doesn't just say something weird will happen. It predicts that when you force that timeless ion to rejoin our timeline, it will release a tiny but measurable burst of heat. The math gives a precise number for that energy release. This makes it an incredibly specific, falsifiable prediction. If physicists run this experiment and detect that heat, it would be powerful, powerful evidence for this new picture of reality.
And so, we've come full circle. The problem of quantum gravity, the mystery of time, the enigma of measurement, they all seem to stem from the same flawed assumption, that we are somehow separate from the universe we're studying. The moment you put the observer back into the heart of physics, not as a passive bystander, but as a fundamental component, the paradoxes just seem to dissolve.
Which leaves us with one last kind of staggering thought. For centuries, science has been about pushing humanity further and further from the center of things. But if this framework is right, it brings us right back. It suggests that consciousness, observation, the simple act of participation, they aren't just random byproducts of a cold, empty universe. They might just be the very things that give it structure, meaning, and maybe even existence itself.